first thing we're going to be looking at is we're going to be looking at the solubility part of this topic, and that has some really important ideas in it. One is that not everything is insoluble, as we used to say. So we used to say that things like carbonates are insoluble except for the sodium ones and the potassium ones. And now we're saying actually it's not quite true. Any carbonate can be dissolved a little bit. Just like the hydroxides, it's not just the sodium, potassium, ammonium hydroxides that are soluble. All of them are to some degree. This part of the topic will focus a lot on things that are what we call sparingly soluble. So they don't dissolve very well, but they do dissolve. Okay? So we're not looking at things like sodium hydroxide, which dissolve brilliantly, because it's too hard for us to get what we call a saturated solution. When we do try and dissolve something that is what we would have previously called insoluble, so now we're saying sparingly soluble, we can do a dissociation equation for it, so we can show it dissociating when it's put in water. Dissociating means turning into its ions, but because it's sparingly soluble, rather than it being an arrow, it's an equilibrium expression. So we get this here. So it's a dynamic equilibrium. As every particle of barium hydroxide in this example turns into barium ions and hydroxide ions, at the same rate, barium and hydroxide ions recombine to make that precipitate. We observe no change. We don't see any change. We have a solid at the bottom of our beaker or test tube or whatever, and we have a solution above it. And the solution above it is what we call saturated. It cannot take any more of those ions into it without making more precipitate. So we get a dynamic equilibrium. The two reactions are occurring at the same rate, but we observe nothing because their rates are equal. And this is where last year when you looked at Le Chatelier's principle, that might come in. If I added sodium hydroxide to this, I'd increase the amount of this because of the common ion effect. I'd be adding more hydroxide ions with sodium hydroxide. So it would drive the equilibrium this way to try to undo the change that I made. So Le Chatelier's principle still comes into it. It would increase the mass of your solid. It would precipitate. So that's worth keeping in mind. Now, because it's an equilibrium equation, we can have an equilibrium expression for this. And we call that the solubility product, or Ks. It might be easier for you to think of equilibrium constant being Kc. So this is a solubility constant. And a lot of people they'll write that. If you write that in an exam, it's okay. It's not 100% correct. It's meant to be called the solubility product, but that's okay. And you'll notice that it's linked to this equilibrium equation. Solids are not included in an equilibrium expression, and nor is liquid water, so we can leave those two out. So all we're looking at is the concentration of barium ions and the concentration of hydroxide ions. That actually means that we can use this value. If we know the solubility of it, how well it dissolves, we can use the concentration of these ions to calculate the Ks value for it. Conversely, if I know the Ks, I can actually find the solubility of something without even having to try to dissolve it. I can do it theoretically and then use an experiment to prove that I'm right or find that I'm wrong and think of reasons why. So the example I'm going to give you is from page 167 in your continuing chemistry book. So if you are looking for this, because it's not very clear on the video, 167 is going to be the one we're going to use. Here, we're looking at solubility. We're going to find the solubility of another carbonate. That's why I use carbonate here, of silver carbonate. Or is it? Sorry, it might actually not be silver. Sorry, it's silver chromate. Okay, we've got to find the solubility of that. And we're given the Ks, or solubility product, for it. So we're told in the question that the Ks of this equals 9.0 times 10 to the negative 12. Notice there's no unit. There are units for this, by the way. We just don't need to remember them. Okay? But solubility, we need to know, is always given in moles per litre because it's linking back to these here, which are concentrations. Okay, so it always goes back to moles per litre. Then you'd have to use your NCV and your NMM triangles to try to get back to grams per litre and that sort of thing, if that's what the question was asking. So you still need to remember these relationships. So you need to remember these as well. Okay. In this question, I'm only going to go to the moles per litre. I'm not going to go to the grams per litre because you haven't been told enough information to do those, like the molar mass. If the molar mass is in there, you'd be able to work out grams per litre, that sort of thing. Okay, so given that, believe it or not, that's actually enough information to answer this question. What we've got, it's actually enough if we want it in moles per litre. The first thing I'm going to do is I'm going to write the dissociation equation, because then I can write my Ks expression, or my solubility product. So I've got this little expression here. I'm only worried about the aqueous things. Remember, this topic is called aqueous solutions. If it's not aqueous, we probably don't care about it. Okay, so there are two things in here that are aqueous. And I'm also going to be able to turn these into a Ks expression. Don't worry about those because they're not aqueous. So I've got this here as my expression. So now I've got the nuts and bolts of this. Here's where the algebra comes in, sorry. We don't know this number. We don't know it. We don't know this number, but we do know the relationship between them because we have a balanced equation. Every one of those means there'll be two of those because of the two in front of this one. In maths, if I have an unknown, what usually is the first symbol I use for unknowns? X. Okay. You can use X, S, L, M. I don't really care what you use. I use X because I think of this as a maths process. Some people use S because it's about solubility. I think they're probably the two most sensible ones to use. I'm going to use X. Your book uses S. Okay? I use X because I think of this as maths. So I'm going to say my lowest common denominator is this one. It's got no numbers in front of it, so it's X. X moles per litre. I don't know what it is, but it's X moles per litre. It's what I'm being asked to find out, actually. So if this has got a 2 in front of it, it would be 2x. Okay? So 1x of those that can dissolve has made 2x of those and 1x of those. Yep. Okay. That's why it's equilibrium, because it's not balanced with what's on the left-hand side, just with the mole ratio on this side. So I now substitute those numbers into here. So I'm going to go my 2x goes into here, and if I look at this, it says to square it, and this is x, so it's going to be times x. 2 squared is 4, x squared is x squared, but x squared times x would be x cubed. Good with that? Okay, so I get 4x cubed. So my expression is 4x cubed equals Ks, which we're given the number for. 9.0 times 10 to the negative 12. So I do a bit of simple maths. I try to remember my bed maths, or however you've been told to learn it. Okay, I'm going to divide both sides by 4 first of all. Okay? So it becomes x cubed equals, and my brain's hurting, 1.25 times 10 to the negative 12, I think. 2.25, yeah, of course it is. Thank you. And then my next step, your calculators do have a cube root button, so let's use the cube root button. And x will equal, here's where I go to look, 1.31 times 10 to the negative 4. So this is only 2 significant figures, so my final answer can only be 2 as well. So 1.3 times 10 to the negative 4. Now, what does x represent? Concentration. So solubility in moles per litre. Okay? So you have to remember your unit there. So This is relying on us understanding that when something is insoluble, it's actually sparingly soluble. A little bit has broken up into its ions. Because of this, it's an equilibrium, so we can write a Ks for that. If we know our Ks value, we can use that information to do some algebra to work out that solubility, and it'll be in moles per litre. If we want it in grams per litre, we then need to start using this triangle here, because that would be a number of moles in a litre, and we'd be after a number of grams or mass in a litre.
If there were two silver chromates in that equation, would we have to divide the concentration by 2?
Yes, you would. However, you don't do that. You do it for 1 mole of what you're starting with always when you write this equation. You always start with the 1 mole of something on the left.
Yeah.
It just makes it, makes it easier.
Yeah.
All right. Any other questions before I stop that?